How do you train an AI to completely ignore a speaker's voice when that voice is literally the only data you have?
Think about it. It's the ultimate chicken and egg problem in speech tech. To understand the words, you absolutely have to filter out the speaker's unique vocal quirks. But to filter out the speaker, you need to know exactly what words they're saying first.
Welcome to Speech World. I am thrilled you're here. Today, we're leveling up your speech tech knowledge by decoding the dense alphabet soup of the classic Kaldi GMM-H model pipeline. We're going to break down exactly how these legacy systems methodically stripped away errors, step by step, to find the pure phonetics hidden inside raw audio. Let's dive right in. Here's our level up roadmap for today. We're going from mono to triphones, fixing our features with LDA and MLT, tackling speaker adaptive training, conquering the two-pass decoding trick, and finally, looking at the complete pipeline. All right, section 1, from mono to triphones. We've got to start at the very beginning with the baseline monophone model. Check out the massive jump in accuracy here. On the left, we've got the mono stage. This is your flat start monophone model. It isolates sounds, sure, but it's completely context blind. Because it doesn't look at the surrounding sounds, it's stuck at a baseline word error rate of about 25%. But look at the right. Enter Tri1. The tri stands for triphones. This upgrade fixes that context blindness by looking at the left and right neighbors of a phoneme. I mean, the k sound in ki is very different from the k sound in ka, right? Triphones capture that difference. Just by understanding context, our error rate drops massively to around 18%. But there's a huge mathematical hurdle we have to jump here. See, if you calculate all the possible left, center, and right phoneme combinations, you get roughly 64,000 possible triphones. No way we can train individual Gaussian mixture models or GMMs for all of those. Most of them we'll never even see in our training data. So how does Kaldi solve this? Senones. Linguists create phonetic questions like, is the sound to the left a vowel, or is the right sound nasal, and they use a decision tree to cluster similar triphone states together into what we call Senones. This brings 64,000 totally unmanageable possibilities down to a neat 3,000 to 5,000 Senones, with each cluster sharing a single GMM. Absolutely brilliant. Moving right along to section 2, fixing features with LDA and MLT. Tri1 is great, but its default 25 millisecond audio window is way too narrow. It just can't see how the audio actually evolves over time. So we enter our next level up, the Tri-12 stage. Let's walk through this upgrade step by step. Step 1. We take our standard 13-dimensional audio frames and splice 9 consecutive frames together. This creates a massive 117-dimensional supervector. Step 2, 117 dimensions is way too bulky, so we use linear discriminant analysis, or LDA, to project those dimensions down to a sleek 40. Finally, step 3, we apply a global rotation called MLLT. Now let's unpack why these specific numbers and steps matter so much. It all comes down to the number 90. Splicing exactly 9 frames with a 10 millisecond hop between them captures exactly 90 milliseconds of audio. Why 90? Because typical phonemes last between 50 and 100 milliseconds. That 90 millisecond window is the absolute perfect sweet spot to see a phoneme's dynamic trajectory without blurring into distant, unrelated phonemes. Now for the analogy. Think of LDA on the left as taking different types of objects and separating them into distinct, highly visible piles. It reduces the dimensions, but maximizes the separation between our phonemes. However, our model relies on diagonal covariance GMMs, which strictly assume all feature dimensions are completely independent. If they aren't, the math completely breaks down. That's where MLT steps in on the right. It acts as a global rotation matrix. It takes those distinct piles and carefully rotates them so they fit perfectly into a neat square grid without any overlapping correlations. So LDA isolates the phonemes, and MLT decorrelates the dimensions so our mathematical models fit them perfectly. Boom! Error rate drops down to 15.5%. All right, section 3, speaker adaptive training. Let's see how we stop our GMM from wasting its capacity on speaker traits. Even though our Tri2B features are amazing, the GMM is still wasting half its computational brainpower trying to figure out if the speaker is male, female, or a child, instead of focusing on the actual words. To fix this, we use speaker adaptive training. And listen, here is a classic interview question trap, so let's clear it up right now. Never confuse fMLLR with SAT. fMLLR is the actual mathematical transform. It's a specific, per-speaker adjustment.
SAT, on the other hand, is the training procedure itself. It's the loop where the system alternates between estimating that fMLR transform for a speaker and then retraining the GMMs based on that newly cleaned data.
And here is the magic fMLR formula, O equals A times O plus B. It's an affine feature transform. A is a 40 by 40 matrix, and B is a 40-dimensional vector. That means we learn roughly 1,640 numbers perfectly tuned to a specific speaker. When we run a speaker's audio through this equation, it literally maps their unique, quirky voice into a shared, canonical speaker space. Suddenly, everyone sounds mathematically uniform to the model, which lets the GMMs focus 100% on the phonetics.
Which brings us to Section 4, the two-pass decoding trick. This solves the ultimate boss fight of inference. Remember that chicken and egg problem from the beginning? How do we decode audio when the decoder requires the audio to already be decoded? We use the brilliant two-pass decoding trick. Pass 1, we do a rough initial decode using a non-SAT model, like our tree-to-be model. This gives us a lattice, which is basically a web of soft probabilistic alignments. Step 2, we use that lattice to estimate our test speaker's unique fMLR transform. Because a lattice gives us soft probabilities rather than a single rigid guess, it's highly forgiving of any mistakes made in Pass 1. Then, Pass 2, we take those newly adapted fMLR features and completely redecode the audio from scratch using our highly accurate SAT model. Quick pro tip for your next tech interview, two-pass decoding is entirely different from lattice rescoring. Notice the stark contrast here. Two-pass decoding completely throws out the old evaluation and redecodes the audio from scratch because the underlying features have physically changed via fMLR. Lattice rescoring? No redecoding. It just updates the math, like upgrading to a stronger language model, on the exact same lattice paths. Let's tie it all together chronologically. Imagine a user, Sarah, speaks into a Try3B system. Time 1, Sarah says the cat sat, which generates, say, 300 frames of audio data. Time 2, we splice 9 frames together to get context and apply our LVA and MLLT matrices to isolate and decorrelate those phonemes. Time 3, we run her Pass 1 decode with a baseline model to get our rough lattice. Time 4, we use that lattice to estimate Sarah's unique fMLLR math, translating her voice into the canonical speaker space. Finally, time 5, we do our Pass 2 decode from scratch with the SAT model, dropping our error rate down to a highly optimized 13%. And finally, Section 5, the complete feature pipeline. Let's step back and look at the big picture. Look at how methodically this evolutionary level up strips away errors. We started at mono with a 25% error rate. We added context with Try1 to get to 18%. We fixed our temporal features with LDA and MLLT at Try2B to hit 15.5%. And finally, we removed the speaker entirely with SAT and fMLR at Try3B to reach 13%. The absolutely crucial takeaway here is that every single stage bootstraps off the alignments of the previous stage. You literally cannot train SAT without Try2B alignments. It's a strictly sequential masterclass in engineering. To round out your knowledge, here's your final rule of thumb regarding decoding. Two-pass decoding is strictly tied to fMLR features, not the model architecture. Mono, Try1, and Try2B. Single pass. Modern end-to-end systems like Whisper. Single pass, because the deep network handles speaker variation implicitly. But if your system uses fMLR features to normalize the speaker, whether it's an old GMM-HMM or a deep neural net, you absolutely must use two-pass decoding. The Kaldi pipeline is a masterclass in removing variables until only the pure phonetics remain. But with deep learning models now handling this implicitly, do you think we'll ever need to manually engineer features like this again? Or is the black box here to stay? If you found this helpful, make sure to subscribe to Speech World for more. See you in the next one.